Hi, so this will be a presentation and a demo of my audio visualizer program, which I made for my computer graphics class at Concordia University this past winter. So quickly, there's going to be a slideshow about me going over the theory of my audio visualizer and the signal processing that goes into it, and then there's going to be a demo. So quickly, this was an application that so the project for this class was very broad. We could do anything as long as it was an interactive OpenGL project. So this application was coded in C++, and the rendering was done in OpenGL. So hi, I'm Adrian. Here are some pictures of me. Can't wait to present that in person. So I submitted these slides already, so I don't really feel like changing them. So yeah, quickly, problem overview, audio visualization. So I wanted to make an audio visualizer for this class. You may have seen some audio visualizers on YouTube or in like Windows XP on the music player program. So you may have seen something like this on the top right, something very psychedelic. So I'm not sure how that works, but I'm pretty sure it's some very complex math. What I'm going to be focusing on, and what I focused on for this application, was the classic bar representation, and this is very intuitive. So you have a bunch of bars. Each bar represents a frequency range, and then the height of that bar represents the amplitude of the waves in that frequency range, the combined amplitude, so the loudness of those frequencies. And then here in the middle, it's actually the exact same thing, but there's a 3D effect because you can see the history of the waves, so the waves in the past. So quickly, we have to address something, which will be, this might be intuitive for some of you guys, but we have to ask the question, what the frick even is sound? So quickly, sound is just a series of compressions and expansions in the air. That's it. And we can represent this as a wave or a graph. And this is what resembles a sine wave, but in real life, sound is not going to look like this. It's going to look very complex. We can't represent it as a single sine wave. But sine waves will be important later. So the next question, how do we store and play sound then? So this is kind of interesting. So how sound is stored is literally just as so it's a single sequence of numbers, and those numbers represent the position that the speaker head needs to be in to replicate that sound. So the computer will read these numbers and move the speaker head quickly, and then this will recreate the sound. And that makes sense because by doing that, you're kind of recreating those expansions and contractions in the air. And then speakers work in a similar way to record sound. So there's something that moves depending on the sound, and then that records the numbers. So yeah. So sound. So we're working on a computer. Computer can't store an infinite amount of data. We only have a finite number of bytes. So we sample the wave each time at a specific time interval. A small time interval, we're gonna make note of the position of the wave, which, like the sound. Yeah, so there, you can go deep into sampling, but that's how the wave is stored. It's sampled like that. This is what's called a time domain representation because the x-axis is time and the y-axis is the position of the speaker head. So you get something that looks like what you have on the bottom left here. This is what you have in Audacity. So the two waves for the left and right audio channels. So that's another important thing. You have two channels because there's a left and right speaker, and you want to create a kind of 3D spatial effect doing that. So next question. Wait, how are multiple frequencies / notes stored in a single wave? I also found this kind of interesting. So like someone plays a piano chord, but it's a single wave. How does that work? Shouldn't it be multiple waves or something. You can have an entire band, so Harry Potter and the Ska Band. So what actually happens is these waves are combined in the air to form a more complex wave. So the expansions and contractions. So say I'm in a room and then there's like a guitarist on the other side of the room playing his guitar. I'm speaking and the guitarist is playing his guitar. The expansions and contractions from my voice and from the guitarist will go into the air and then they'll combine, and then they might go into like a microphone or something. So that's how that works. So how do we find the frequencies and their amplitudes? Because what we have are we just have a single sequence of numbers. We have the position of the speaker head. How do we get the actual frequencies from that? So we have to think in waves. So what we have to understand first is that to get our final wave, we're just combining a bunch of different sine waves, and each sine wave is just a pure wave representing a specific frequency. So a bunch of different sine waves, more than 3, each of a different frequency. This image summarizes everything basically. So we have a bunch of different sine waves combined into our sound wave in time domain, and then here the amplitude of each of these waves is what we're looking for. These will be the heights of the bars. We'll have a lot of these, and in my program I'm going to combine a bunch of these bars to make like a bigger bar. It's done with some very complex math called the Fourier transform, which even I don't really understand fully. You'll see in my demo that the wave I get, it looks kind of weird, and I think that's because I might be misusing the library which I use, which was FFTW. Because with this library, it's a kind of low-level language. It's not like I'm using a Python library where I could just do like .get wave frequencies and then it would work. You need to kind of do stuff yourself and understand what's going on for it to work properly. Yeah. So quickly now, I'm gonna give an overview of my application structure. So the first thing that needs to happen is the audio samples need to be loaded. Then I create my SFML window. And what I did is I created a custom audio streamer class, which is extended from the SFML audio streamer class. And what it does is it plays the audio, and then after a specific number of samples has been read, which I specify here in the period, it will analyze those samples and perform this Fourier transform on them right here to get the amplitudes of the frequencies. Here's a screenshot of some of the OpenGL stuff I do. So creating the VAO, the VBOs, loading and compiling my shaders, the projection matrix for my camera, setting up the GUI. So how this works with the bars is that I have 2 VBOs, one for the 2D bar, which is just a square, and one for the 3D bars, which is just a cube. That's it. And to render the different bars, I basically calculate a bunch of model matrices to scale and to move the bars around. So here's what my main program loop looks like. So I handle the events, calculate the height, amplitude for each bar, because I have my period at 2048 samples, and what that works out to is that I have 512 different frequencies that I actually have, but I might have like 10 bars, so I need to combine a bunch of those frequencies into bars. So that's what this is. View matrix for the camera. For each bar, calculate the model matrix and draw the bar. Not drawing the light source, I remove that, and then I draw the GUI. So here are the libraries that I used. This image is just because I wanted to use IamGUI, and I wasted a lot of time trying to get it to work, but it just doesn't work. And then I later discovered an open issue where it says that OpenGL 3 doesn't work with IamGUI. IMGUI SFML, which is the library that integrates IMGUI and SFML. So yeah, it was a futile effort to begin with. Here are the goals I outlined in my project proposals. Audio capture just means capturing the audio or loading it from an audio file. I wanted to capture the audio. Another thing I wanted to do was capture the audio from like the line out of the computer. So I could be playing Spotify and then my application would visualize it. I had managed to do that. I might in the future. I know it's possible because there are other audio visualizer apps which can do that. Audio processing means doing the Fourier transform to get the amplitude of the different frequencies. 2D visualization is just 2D bars. 3D visualization is just the same thing but with 3D bars. And then the 3D model visualization meant rendering a model and then manipulating that model based on the frequencies. So yeah, demo time, about time. So what time am I at? 11 minutes, okay. Gonna need to speed that up for the actual demo. So I think this is about 25 bars. So this is the 2D bars. You're looking at it kind of up, looking down, just this is the way my camera is set up. I can spin it, and you'll notice that the color kind of changes because I implemented some basic diffuse shading. The light source is right above, so that's kind of weird. And then I can have the camera spin around, so it spins around the y-axis. Yep. And another thing I can do is amp up the number of bars. So I can set 100 bars. I can set the size 512 bars. That's what that looks like. Spin it. Let the camera fly around. So, yep. And then there's the 3D mode. So these are 3 bars. Looks a bit weird because again the light source is right above it. I can spin it. I can have the camera fly around. You can also set the spin angle and the fly angle. So one. So this is back to and then a very cool thing I implemented is the circle mode. So this renders. It positions the bars in a circle. Spin and have the camera fly around. Amping up the number of bars. So as you notice, there's a lot of so the bars near the low end of the spectrum are very high, and I think that's just because of me misusing the library. I would really like to go back and try and get the bars to be more evenly spread. I like the actual heights of the bars to be more evenly spread out. So yeah, the final thing is the monkey. Here I'm rendering the Suzanne head from Blender, the default model, as a wireframe. And then what's actually happening is each vertex is kind of mapped to a frequency, and then the vertex will move up along the vertex normal depending on the value, the frequency value. So the eyes kind of go crazy because I think they're mapped to the low end of the spectrum, and then the ears are mapped to like slightly above that. So yeah, that's that. The model visualization is not perfect. There are some vertices that don't move. I don't know. I'm not sure if that's a glitch or not. The way I did it is actually very stupid. I should have done it in the vertex shader, but what I did is I calculate the vertex positions, and then like I recalculate the entire vertex array, and then I replug that in. It's very stupid. But yeah, that's about it. Hope you enjoyed watching. Have a good one.